Hello everyone, I'm Onurcan and today I will be talking about my METU EEE star research project on deep iterative construction for phase retrieval. This research was supervised by Associate Professor Unrolling. Let me first start with problem definition. This inverse problem is about finding the unknown image X from its noisy Fourier intensity measurements. And if we have an n-dimensional image and if we have an m-dimensional Fourier intensity measurement of it in our stuff, we will use m equals 2n for uniqueness guarantee, and the noise will be modeled as a Gaussian noise. This problem occurs in many places like crystallography, microscopy, since they all involve taking the measurements of the intensity of a Fourier transform of an object. I will focus on a specific application, namely lensless imaging. As you know, in traditional imaging we use lenses to create an image of the object, but this maximum resolution is limited by the diffraction limit, and due to this limit, to view the tiny molecular structures we can't use optical region of the spectrum. We should use X-rays to investigate the structures of tiny molecules, and we have no efficient lenses working in X-ray region, so we should try something different. And one way to solve this problem is coherent diffractive lensless imaging. We can record the intensity of the field in far field, and we can then understand the objects and structures by computational imaging. In traditional imaging with the lens, if we illuminate the sample by a uniform plane wave, we get exactly the same thing in the observation plane with the object plane, ignoring the flipping and diffraction limit. So these lenses create a perfect image. But in lensless imaging, after we illuminate the sample, we get a far field propagated intensity like this one. But this propagation actually corrupts the field. I mean, this propagation causes the sample to become unrecognizable, and we want to backpropagate the recorded intensity of the fields. Here, if we can backpropagate, we can actually reconstruct the sample transmission function. But our field is complex. It has both amplitude and phase information, but we can only measure the intensity squared amplitude using our CCD sensors, for example. So lensless imaging requires phase retrieval, and we know from the Fraunhofer propagation the far field intensity is proportional to magnitude of the Fourier transform of the object. So we know the support constraint, we know the intensity, which is the squared amplitude of the Fourier intensity, squared amplitude of the Fourier transform of the transmission function. So we want to find the transmission function using these two known constraints. So by knowing these two constraints, support constraint and intensity constraint, we find the Tx satisfying both constraints. Classical methods to solve this problem: first, guess object satisfying the support constraint. Then we will calculate the Fourier transform of the guess, so we propagate the field physically. Then we will enforce the intensity constraint. Then we will backpropagate it physically. I mean, we will calculate the inverse Fourier transform, and we will enforce the support constraint, and we will repeat this step. After iterating through these steps, we can find the following reconstruction after 4,000 iterations. As you can see, this reconstruction is not good. So instead of directly enforcing the support constraint, we will do something different. Instead of this, we will also add a feedback function outside the support in the algorithm, and the reconstruction will be better if we do this feedback step. As you can see, it's much better than the error reduction algorithm, which is the first one. So to understand them intuitively, we can use the geometrical interpretation. We have a set of all transmission function txy satisfying the support constraint. We have also set of all txy satisfying the intensity constraints, and we want to find the solution, which is the intersection of these two sets. And ER algorithm actually alternatingly apply these two constraints. This enforcement actually corresponds to projection operation geometrically, since it finds the closest point in this set. So it alternatingly applies these constraints, and the error reduces in each step, as you can see. But we don't actually converge to a good reconstruction, and the reason for this stagnation actually is non-convexity. The previous picture is very misleading, since the intensity constraint is a non-convex set. So this picture is better than the previous picture, and as you can see from this picture, it will stagnate at a local minima. And actually this is not a good reconstruction, since we will this. And your algorithm uses projection operation, as we saw, and here algorithm, instead of projection in here algorithm, it actually uses reflections geometrically. You can also understand the classical method from an optimization perspective. We want to minimize the following cost function. So if we apply the gradient descent algorithm to solve this problem under some assumptions, we actually derive the error reduction algorithm. But the problem here is that gradient descent actually converges to a local minimum. Since it converges to local minima, we can't find the global minimum, but it actually reduces the error in each step. So as we saw in classical methods, the resulting reconstruction are not very good. They have some artifacts, and they can stuck in local minima, and they can amplify the noise. So we should do something different. One modern method to solve phase retrieval problem is applied optics method. In this method, we first initialize the image by this initialization step. In this initialization step, we first randomly initialize by using Q algorithm. We try different initialization and chose the best one among them. And after choosing the best one, we will iterate the Q algorithm 1,000 more times to find the following reconstruction. And after initialization step, we will use iterative DNN HEO stage. In this stage, we repeatedly do this denoising and HEO step. After we denoise the result, we will enforce the constraints using model HEO model. Then we will repeat this iterative stage at most 30 times, and we will also use a final denoiser to improve the reconstructions at the output of the iterative stage. Note that these denoisers are CNN-based denoisers, namely FPV COMNET, and they are trained using ground truth image. And for example, for training DNN1, we will use the results of the initialization stage together with the ground truth image, and to train the DNN2, we will use the results of the iterative stage together with ground truth image. As you can see, it has a much better reconstruction quality than the HEO method. And what I do in my project is to implement this applied optics method in Python. And actually, it is a faster implementation than the MATLAB implementation. And I can now try different approaches in Python. I also tried different loss functions like L1 loss. L2 loss, I mean mean squared error loss, actually smooths the output it gives us a low pass filter, denoisers, I mean, and this actually eradicates the fine details in the images, but we want to preserve these fine details, so L1 loss can be very helpful in this perspective. So I trained with L1 loss, and I tried both DNN1 and DNN2 denoisers using L1, and I tried to find the best combination of the training functions. As you can see from this table, the best combination is to use L2 loss for training of DNN1 and using L1 loss for the training of the DNN2. And you can see from here visually. I also tried using different denoiser architectures instead of SPV CONET for DNN1, but the results were not very promising. They are not different, and I didn't continue to try different denoisers. I also tried different number of Hill iterations in iterative stage, and I observed that with very small alpha values, this can enhance the reconstruction quality, since the measurements are very good. This is as expected. And I also tried to improve another modern method, PRDIP, which uses FASTA to solve the PR problem. I tried to improve the reconstructions of PRDIP method by using an additional denoiser. Even if I don't train it for PRDIP reconstruction, this actually gives better results than original PRDIP results. So this is very promising. As you can see, using an additional denoiser at the output of the PRDIP actually improves the reconstruction quality. And you can see the average reconstruction performances here. And to understand my motivation, we should look at the results for iterative stage and PRDIP results. PRDIP actually gives better reconstructions than the iterative stage, and I thought that we can improve these results using an additional denoiser. And I tried it, and it gives the following results given in the table. It actually improved the reconstruction quality of the PRDIP results. I also tried multiple DNNs approach. In this approach, a network consisting of 3 different sub-FPV CONET denoisers has been implemented and jointly trained in Python. I divide the iterative stage onto 2 subparts, and these 2 subparts uses different denoisers, different network parameters, and I train them using the following code functions. This code function gives better reconstructions when I tried, since it is important to have a good output at the end in this loss function. And the results show that the new multiple DNN approach is superior to the applied optics method, as you can see from this table. And we can see it visually. As you can see, this is the result for multiple DNN approach, and this is the result for the applied optics method. And we can see it from this image also. And if we zoom onto the images, we can actually see it much easier. As you can see from these images, it preserves the fine details in the images better. And you can see the histogram of the Monte Carlo simulations from this figure. So I also tried unrolling approach. And the main idea here is to unroll the optimization iterations onto a neural network. So our problem is given here. So if we can write an optimization problem, we can find optimization iterants, and we can unroll them onto a network. So to model the optimization algorithm, we will use map estimation. And using HQS, we will end up with the following sub-problems. And these sub-problems have the following closed form solutions. But we can actually replace this data consistency step with HEO algorithm, and we can use a deep denoiser in this step. And the following algorithm is given here. We can unroll the steps of this algorithm onto a neural network, and we can train it. This neural network has the following basic block. In this basic block, we have a denoising step, which we use CNN-based denoiser, and we have also a data consistency layer, which we use HEO algorithm, and we combine many of them in a network and train this network. Also, we should also note that this x0 is initialized with the same procedure used in the apply of this method. So the results can be seen from here. As you can see, it improves the HEO constructions. This is after initialization, and this is the final result. It's much better than the HEO reconstructions. Also, you can see from here or here. It's also better in terms of SSMI and PSNR values. And you can see the average reconstruction performances from this table. I also observed that using more layers, I mean using higher K values, give better reconstruction quality. And you can see the results for K equals 7. I am now trying higher K values. I also tried using shared phase in Unrolling method and in multi-DNN methods, as I mentioned previously, but it didn't help. It can be due to nonlinear and non-convex feature of the phase retrieval problem. So to sum up, classical methods like HEO do not work very well under noise measurements, and they generally converge to a local minimum by creating artifacts. But methods utilizing deep neural networks are very successful in terms of reconstruction quality with respect to classical methods. And using different training functions like L1 loss can improve the reconstruction performance, and jointly training the multiple networks is a very promising approach. Unrolling idea is also very promising. Thanks for your attention, and here is my references.